Okay. All right. So the equation of a plane, specifically Cartesian. Okay, so it's quite all right, so it's hard to draw. So if I have a plane such as this, so for this example, the most usual example is we're going to find the equation of a plane, and to do that we need a point on the plane, and we need the normal vector to the plane. So this is imagine this is a three-dimensional plane. So let's just say we've some point here, A, I'm going to use 3, 2, and 5 to suggest that point. And then we have a normal to that plane, so like it makes a right angle here. It's a normal vector. Okay, so the normal vector will always be perpendicular to the plane. Let's give that n, and let's call it 1, minus 5, and 4. Okay, so there's a very direct relationship between the normal vector and its plane equation, which I don't know if you've come across recently, but you'll see it in the answer at the end. But for this, we're going to look at one of the formulas or two of the formulas in the formula booklet. There's this thing called or dot n is equal to a dot n, which I don't think I went into much detail on the last time I did vectors, but we'll look at it now. So let's make another vector somewhere, anywhere in this plane, and just call it x, y, z. I'm going to label it or, because or and a, you'll see that now in a second, why just to match the ones that are in the formula booklet. So x, y, z is our known point. So it could be any point on this plane, doesn't necessarily have to be near the normal. It could be here, here, here. Okay, so we're going to look at a to or then. Okay, so how would we get the vector a to or? That would be, well, from our basics of vectors, that would be o or minus oa. Hopefully you remember that one.
Yep.
Okay, so also that would be just then their position vectors, wouldn't it? Because it's from O. So we could just call it or minus A, the position vectors of those subtracting. That's because O is just going to be zeros. Okay. And this or minus A would also definitely lie on the plane, wouldn't it? Because
both points are on the plane, yeah.
Yeah, okay, so, all right, we're on that stage. So, if this is then a vector that's on the plane, and we have a normal here, we're going to use the angle between the normal then and this vector, the two vectors, the angle between them. And this is going back, of course, the angle is 90 degrees, and therefore is perpendicular. And we can, we then know that the dot product or scalar product of those two vectors would be what?
Of the normal and AR?
The normal and this one. If we know that the angle between them is 90 degrees,
then it's going to be 0.
It's going to be 0. So therefore, we can say or minus a dot product n is equal to 0 from what we were talking about yesterday. And of course, if we expand this out, that'd be, just use the distributive rule, that'd be or dot n minus a dot n is equal to 0, and therefore or dot n is equal to a dot n, which is where this thing comes from.
Okay.
Now, how does this help us find? This helps us find the equation of the plane, the Cartesian equation of the plane. So if we know a vector, or a point, sorry, on the plane, and we know the normal, this equation will help us find the equation of the plane. So we do the scalar dot product between aura and n. So aura is x, y, z, and n is 1 minus 5, 4. So that'd be x times 1, y times
-5.
5, okay, and z times 4. No, I should write 4 times z is the same. And then we actually know a then when we do 3 times 1, 2 times -5, and plus 4 times, no, we're doing that right? Yes, 4 times 5. Okay, so, just squeezed in the page. All right, when we work this out, x times 1, so that's going to be x minus 5y plus 4z, and that equals a number. And I have this done already, so that's 13. So if you work that out, that would be 13. And that is the Cartesian equation of the plane.
Okay.
And notice the difference between, or the similarity between that and the normal vector.
Oh, yeah.
Okay, it is just this number we need to create. And that is so it's a little unusual if you compare it to the equation of the line, deals with its parallels, slopes, but the equation of the plane deals with perpendicular slopes in a way.
Yeah. Wait, the dot product, if they're perpendicular, will give you 0, right?
Yeah.
Isn't OA perpendicular to the normal equation? But when you multiply A by the normal,
Isn't OA this one?
yeah, which is just the same thing as A, isn't that perpendicular to the normal?
No, not necessarily.
Okay.
Is O on this plane then? Is that what you're saying?
Oh, right. We don't know where O is. Okay. Yeah. Okay.
Yeah, O could be over here somewhere.
Yeah. Okay.
Yeah,
That makes
and
sense.
then, but we're just using its relative position to.
Yeah, I just
find
assumed
order.
that O is on the plane. Okay.
No. Okay. All right. So therefore, the vector product gives us. No, that's not therefore. Why have I made that note? Oh yeah, so you can work backwards and get the normal vector if you have enough information here. And we look at an example. Is that the example I did? Normal vector. No, it's not the example I did. Okay, I'll have to create another example to show what I made a note of, but I didn't have an example, so I'll come back to that on Thursday. Okay, so that's the basics of equation of a plane in Cartesian form. Now we're going to look at the intersection of a line and a plane. Okay, so let's say we have 2 points, first of all. Like, they actually don't give us the line, just say, all right, here's 2 points, 1, 4, and 2. And here's 4, 6, and 3. So it says, where does the line between these two intersect a plane? So let's use 2x plus 3y minus z is equal to 34. So you should be recognizing now at this stage that we can already find the normal to this plane straight away. It's just there.
Yeah.
Okay. So where do they intersect? So in order to find where they intersect, we must need to find this line between A and B. So how do we do that?
Take one of the points first, and then that'll be the first vector.
Okay, so let's just 1, 4, and 2.
And then we do the next vector will be CB, which will be 3, 2, 1.
Yeah. Okay. 3, 2, 1. All right. So that is our vector equation of the line. So let's turn that into. For this, it'd be, I think, beneficial for us if we have x, y, and z. To turn into a Cartesian or parametric Okay, so let's turn this into our parametrics. So x is 1 plus 3t, y is 4 plus 2t, and z is 2 plus t. So have you any suggestions, Sean, as to what I might do next to find where these
Substitute
two?
them in.
Yeah, it's as simple as substituting in. So I'll show you very briefly. So we have values for x, y, and z, and it should satisfy the equation at some point. Or hopefully will intersect the plane. Should it intersect the plane? Will it always intersect the plane?
Okay, in this case, it won't intersect the plane if it's parallel to it, right?
Yeah, so that would be the only case. So otherwise, it should intersect. Same as lines, I suppose, in that way. Yeah. Did you watch the video, by the way, that I put?
I have not watched it yet, no.
Okay, so do watch it, and there's multiple links off that video that are. That's one of the more complicated. It's based off a that's kind of university standard matrices maths, which would have been an option in the old HL course, but it's good for visualization, and there's a distinct link between vectors and matrices. But it's interesting to explain what I was trying to show you yesterday about the right-hand rule and stuff like that. I think it's a lot clearer than me trying to do it on screen here. So it'll have a look at that.
Okay.
Explain yesterday's and coming out of the screen and towards the screen and stuff. Okay, so just multiplying this out and we will get a value for t. So I'll just take you to that stage. 11t plus 12 is equal to 34, and then t is 2. So answer, that's not our answer, obviously. How do we find the point then?
We sub 2 into t for the line equation, and then we just find that.
Yeah, exactly. So that's not the answer, but if we do sub t into 2, we will get it, because we know x, y, and z would be 1, 4, and 2 from the, I'm taking the line equation here, plus now 2 times this, and that would be the point in time that they meet, or time is that parameter. 3, 2, 1, and then work all that out. So x would be, I'll just do the x1. X would be 1 plus 2 times 3, which is 7, and so on. Do the same for the other 3. And that is how we get the intersection. So that's another basics of plane and very common question asked, the intersection of a line on a plane and the equation of a plane. All right. So I'm going to do one exam question, and then I'm going to let you guys, Sean can try some of the questions that I put up today. So an example of an exam question. So this will be a difficult exam question.
Okay.
Let's see. Okay, so this is the exam question. Plane has the Cartesian equation. So we just dealt with Cartesian equation. So x plus y plus 3z is equal to 5. Okay. The line L has the vector equation. Or is it 2, 3? Oh, I can't read my own writing. I think that's -1 plus -1, 1, and p. Okay, and the question is the acute angle between L and the plane is 60 degrees. Find possible values for P. Okay. Any idea where you might start here, Sean?
Now let's start by the plane has a Cartesian equation that.
So we've got some plane here. We've got a line that intersects. You can draw this looking three-dimensionally. So it comes through it like that.
And the acute angle between L and the plane, so that means
this
that
angle
one
here is 60 degrees. Okay.
And that means the angle between it and the normal vector is going to be 30 degrees. So find the dot product between that and the normal.
So there's our normal up there, and there's 30 degrees. Oh, good. Okay, so what is the normal vector then?
1, 1, 3.
Okay, so let's put it in IJK form.
Oh, okay.
But it's okay, you can go either way. So that's the normal. We would need then the direction vector, of this.
Yep. Which is negative 1, 1p, or negative I. Okay. Yeah.
Yeah, negative I. Well, we're doing. It doesn't matter yet. Either's fine. So that's the direction vector, which is always the last bit here of L. Very good. So we're going to use the acute angle. So we would need the scalar product.
And we also need the magnitudes of both.
Yeah, we need the two magnitudes. So we're using, if we take our formula booklet, we are going to use the angle between two vectors, because now we have two vectors here. Use the angle between them. We would be able to find it. So we use the scalar product on top. So it's cos of 30 degrees in this case is equal to the scalar product on top, which you can write like n dot d, and then it's the magnitudes of both, on which we looked at yesterday. Okay, so dot product then is the same thing again. Where are we? 1 times minus 1, 1 times 1, and 3 times p on top. So
it'll just be 3p in the end, right?
Minus 1 plus 1 plus 3p. Yeah, you're jumping ahead of me here. And then the square roots of 1 squared plus 1 squared plus 3 squared, which is 11.
11.
And the square root of p. It's going to be 2 plus p squared, or 2 here. Okay, and that equals cos 30. Of course, cos 30 is a known angle. What would that be?
That is root 3 over 2.
Root 3 over 2. And this is solvable from here, and I'm not going to spend much time going into that. You end up at some stage getting root 33p squared plus 66 is equal to 6p if you multiply by 2, and that cancels out and bring it all over. And therefore square both sides, and that's 36p squared, and then that's still that. So you end up with
3p squared equals 66.
Yeah, thank you. 3p squared equals 66, which means p squared is equal to 22, which means p then is plus or minus the square root of 22. So there are the two possible values. P. Yep. So that's an example of what is a difficult vector equation. So vectors can get very difficult. If you go on the online and even watch some of that videos linked beyond where I showed you, they get very complicated, and university style maths used a lot. And actually, if you're going on to do computer science, Sean,
yeah, they love matrices there.
Matrices and vectors would be a key component, especially matrices.
Yeah.
So, Tamara, are you thinking?